Hello, my esteemed viewers. As we enter into tutorial number 4, uh, after having gone through tutorial number 1 to 3, we will derive a simple equation or simple relationship relating the force, the area of cross section, the elastic modulus, and the length of elongation or change in length. And we will also make use of the important concepts like Poisson's ratio, Poisson's effect, etc. to solve simple programs to start with, and the further tutorials will bring the problems of increasing complexity before we finish the first module on simple stress and strain. And Poisson's ratio, of course, is a very important concept. When we pull a component with forces, it will elongate all right, but sidewise it will get squeezed. If we consider a rod of diameter d and of length l, the length l will go for elongation to a bit, and it is increase in the length, while the diameter is going to get compressed, or diameter is going to be decreased. And on the other hand, if we take a component and compress that component, it will bulge or it will squeeze out in the outward direction. Thereby the change in length, in the longitudinal direction there is a reduction in the length, while in the lateral direction it is increase in the diameter. This side effect caused by the force or caused by the stress is also called as Poisson's effect. Poisson's effect is accounted by a ratio called as Poisson's ratio. Let us see as to what this ratio is all about. Within elastic limits, lateral strain is proportional to linear strain. This was the postulation done by Poisson, and if we formalize this postulation or postulate, we will come out with a formula. E lateral, that is epsilon lateral strain is proportional to linear strain. And if we remove this proportionality constant, we will get proportionality limit, proportionality symbol. We will arrive at a constant called as Poisson's ratio. Poisson's ratio is represented by mu or 1 by m, and if you calculate mu, that is Poisson's ratio, it happens to be E lateral by EL. E lateral is going to be very less when compared to E longitudinal. E longitudinal, the strain along longitudinal direction would only mean the strain that is taking place along the length. And it is important to remember longitudinal strain will always be greater than lateral strain. Therefore Poisson's ratio happens to be less than 1. And he is the Simon Poisson, lived during 1781 to 1840, and he is the person who postulated this particular theory, and he accounted for this Poisson's effect. Increase in one dimension brings in reduction in the other dimension. Increase or decrease, and vice versa. Decrease in one direction will always bring in increase in the other direction. Steel has a Poisson's ratio of 0.3, and aluminium 0.22, paraffin, rubber is 0.5, the maximum. Concrete is 0.15, and cork, the bottle stoppers, what are called as, they have Poisson's ratio 0. They, even if they compress it, they are not going to bulge outside, and if you elongate it, it will be into pieces, and even if they elongate, there will be no lateral reduction. Therefore the Poisson's ratio for cork is 0. We will make a simple derivation which can be used for solving our problems, and of course this derivation holds good as long as the material is elastic. Consider a bar and apply the force P. Due to application of the force P, there is a small increase in the length. This dl is exaggerated, of course. Over here it's going to be very small, and we are trying to find out the value of this particular dl. What is the change in length owing to application of a load P on a prismatic member? Sigma equal to, we know sigma equal to, that is stress equal to elastic modulus into strain that we have shown last time, okay, in our last tutorial. Sigma equal to E, and the strain can be written as dl by L, and therefore sigma can be written as P divided by area of cross section, and this remains as it is, and we will get change in length after some simple simplification. We will get change in length equal to PL by AE. Of course, this formula is applicable to prismatic bars or rods that are axially loaded. Being a prismatic bar or being a prismatic rod, the area of cross section is constant throughout, and there are no changes in the area of cross section. And we will go through some illustrative problems of engineering interest, and this particular tutorial will have very simple formulas, simple problems rather, and as we continue our next session and the subsequent sessions, we will try to cover so-called complex problems. And here is the problem goes like this. Tensile test is performed on a brass specimen 10 mm in diameter. When 25 kN is applied, it showed a distance between gauge marks increased by 0.15 mm. If the original gauge length was 50 mm, what is the modulus of elasticity of the brass? And we need to find out the measure of elasticity of the brass using some of the data that is given. The data pertains to the length over which change in length is measured, and change in length is happens to be 0.15. This will indicate that that the member should be subjected to tensile load, and the tensile load is 25 kN, and the bar measures 10 mm diameter. Here is the bar, and it is this is the length over which the strain is gauged, and 25 kN is applied. In reality, the bars or rods will be put up with small electronic strain gauges, and it will be something like this. So modulus of elasticity E is sigma by epsilon, that we know, and sigma here in this case is P by A. P is 25 kilonewton. We have multiplied that with 1000 to make it Newton, into 4. 4 comes from the area that is below, the expression of area over below this particular expression. It is pi d square by 4. This by 4 will go and go to the denominator by inversion. Of course, 25 into 1000, this is the load portion of it, and this is the area, pi d square by 4, and 4 will come up, and this will get us 318.3 Newton per millimeter square, or 300.3 MPa. While the strain is change in length by original length, change in length is given to be 0.15 millimeter, and the total length over which the strain is measured is 50 millimeter, so it becomes 0.003. We would have also placed this strain as 3 into 10 to the power of minus 3. Anyway, strain is unitless, therefore it becomes a number. So the question is finding the elastic modulus. So elastic modulus is sigma over epsilon, that is stress over strain, and stress is 318.3 and strain is 0.003. So that gives us 106,100 Newton per millimeter square, or we could have succinctly placed this as 1.06 into 10 to the power of 5 MPa, succinctly and crisply. Anyway, right. A steel rod 30 meter long hangs and holds 900 Newton weight at its lower end. If the diameter of the rod is 6 mm, calculate the maximum normal stress in the rod considering its self weight. Unit weight of steel is 77 kN per meter cube. And this is the arrangement. Here is a ceiling to which a wire is hung, and at the bottom of the wire a weight is placed, or it is holding the weight, and the length is 30 meter, and it has 6 mm diameter. The rod has 6 mm diameter. So now we need to find out the extension, and here the force is, the applied force over here is 900 Newton, and the self weight of this particular rod. And self weight can be calculated, weight of the rod can be calculated, by multiplying volume of the rod into its unit weight. And volume is, after all, area into length, area of cross section into length. And here we should understand, when area pi r square is repeated over a height, cylinder is generated. In the same token, area into length will give us volume, where length is the length of the rod and area is area of cross section of the rod, into unit weight. Unit weight is given to be 77 kilonewton per meter cube. So area is pi d square by 4 into length is 30. In order to make it millimeter, we have multiplied it by 1000. We have multiplied it by 1000 into unit weight. Unit weight is 77 kilonewton per meter cube. So in order to make it Newton, we have multiplied by 1000. So this becomes 77,000 Newton divided by, in order to obtain millimeter cube, we have multiplied meter 3 times. Okay, a meter, because it is meter cube, 1000 into 1000 into 1000, that makes it 10 to the power of 9, because 1000 millimeter equal to 1 meter. So we have put up the formula and we get the weight to be 65.31 Newton. Therefore, total normal stress is the weight that is attached over here and the self weight, which happen to be 65.31 Newton, and divided by pi d square. D square is 6 square, pi d square by 4 will come to the top, and what we get is the normal stress. This normal stress is owing to self weight. Once again I repeat, self weight as well as the weight attached at the bottom. Then the third problem goes like this. A loading crane consists of a steel girder ABC supported by the cable BD is subjected to load P. Load P is placed over here. The cable has a cross-sectional area of 481 millimeter square. The area, cross-sectional area of this particular cable is 481 millimeter square. So area is directly given over here. The crane is shown in figure. Okay, if P equal to 32 kilonewton, what is the average stress in the cable? If the cable stretches by 5.1 millimeter, what is the average strain? We need to find this particular length using the geometry of the arrangement, and from the mechanics, in order to find the tension, force, and the consequent elongation or whatever that is being asked, we need to find out what is the force experienced by dB or BD. So in order to do that, we need to make use of principles of mechanics, and we need to write the free body diagram. Anyway, our simple consideration will show that this application of the force P over here will definitely generate tension in BD, tension in the cable. So this is length of BD is its square root of 3 square, the base, and 1.6 square the height. It will give us 3.4 meter length. And the angle dBA over here, because we need this, is sine dBA equal to opposite 1.6 divided by hypotenuse. Just now we have calculated. So 1.6 by 3.4 equal to 0.470. Now we will angle dBA is sine inverse of 0.470. Therefore it becomes 28 degree. Now we have written the free body diagram over here. Here is a force, tension force acting away from the joint, and 28 degree is over here, and here is the load, and we take moments over here in order to find T. Okay, because this system is in equilibrium. So 32 into 4.5, 32 kilonewton applied over here into 4.5, the moment arm, minus, because this turns in clockwise direction while this turns in anti-clockwise direction, and it is the vertical component of T which will enable kind of a moment with respect to A or about A. Therefore T sine 28 into 3, the moment arm for this is 3, and we know all the values. Sine 28 happens to be 0.469, and 32 into 4.5 divided by 0.469 into 3, this portion. Okay, when we equate it to 0, we are applying principles of equilibrium. So we get T, that is tension in the wire, tension in the cable, to be 102.34 kilonewton. Tensile stress in the cable therefore equal to 1.2.34 into 10 to the power of 3 or 1000 to make it Newton divided by 481 millimeter square. 481 millimeter square is given in the problem. Therefore we are directly applying and we are finding the tensile stress in the cable 212.8 MPa. Strain in the cable is change in length by original length. Change in length is 5.1 millimeter. Original length was 3.4 meter. Therefore we want to make it meter. So 5.1 divided by 3.4 into 1000. So that gives us 1.5 into 10 to the power of minus 3 as the strain. Strain is unitless, therefore we need not to write anything. Some authors recommend writing this units of the strain as millimeter per meter or millimeter per so many millimeters, millimeters per centimeters. Anyway it's the units will cancel away if you convert into same kind of units. Therefore strain is a unitless parameter. A cylinder, the fourth problem is a cylinder that has a sealed cover plate attached with steel bolts contain a gas under pressure of 2 MPa. The diameter of the bolts that is placed over here is 5 millimeter and the allowable stress in the bolt is 150 MPa. If the that means this bolt can enjoy or can sustain or can tolerate or can bear 150 Newton per millimeter square. Let us see as to what kind of stress it is. If the inside diameter of the cylinder is 100 millimeter, find the number of bolts required. And whenever we say the pressure is same along all the direction. So amount of pressure exerted on this walls of the cylinder and over here and over here, so also on the plate is the same. And due to the pressure, inside pressure, the plate will always have the tendency to blast off or to go above or to move in the upward direction. But anyway, these nuts, these bolts will never allow this particular plate to be flown off or to be just getting detached and moving in the upward direction due to the inside pressure. Therefore they sustain tension. So holding this particular plate instead, okay, in the position, the bolts will suffer from tension. So this would have happened. So it would have moved like this. Therefore it will impart tension on these two bolts. So bolts will be in tension. Where exactly this force is acting? If you consider this is the top plate, from the bottom the pressure is acting. The pressure is from the bottom plate is the pressure at the bottom plate is 2 MPa, 2 Newton per millimeter square. Therefore you can calculate the total force from the bottom equal to pressure into area. As stress is load divided by area, pressure is also load divided by area. We are calculating the force, total force, owing to this particular pressure acting on every point of the bottom of the plate. Therefore it becomes pressure into area of the plate. Area is 2 pi r square, 2 pi d square by 4, 2 pi d square by 4, 2 is the pressure, pi d square by 4 is the area. Therefore what we get is 15,708 Newton as the total force acting from the bottom. Now we will calculate this force is to be resisted by some numbers of bolts. It is not only one bolt. Bolt will be arranged in a circular fashion over the periphery of the plate. Force that can be taken up by a nut, single nut, is allowable stress, permissible stress in the nut, and to area of cross section. So this will be the force taken by a single nut. Okay, and the force that is acting on the nut owing to the pressure from the bottom will definitely keep the nut in good stead, or it will be in working condition or workable, because it will be enjoying workable stress, or it will be happy holding the top plate. Therefore it is allowable stress into area. So 150 is the allowable stress that is given, and area of cross section is pi 5 square by 4, because the diameter of the stud is diameter of the nut is 5 square, 5 millimeter. Therefore this is the area of cross section of the nut which is subjected to tensile force due to the pressure from the bottom, and this will give us 2945. That means each and every nut, each and every bolt or nut and bolt system will be able to sustain a tensile force of 2945 Newton. Therefore, their total number of bolts is a simple thing. Total force to be taken up, it is 15,708, and the individual capability of a nut, that is individual nut capacity, so it is 2945, because each and every nut can bear a force of 2945. Therefore it will get us a number which is equal to 5.33. On rounding it off, it becomes 6 nuts, and nuts can be arranged like this. This is a look, this is a view. If you take the top view of the pressure cylinder, you will see nuts arranged like this in a circular fashion. Okay, 6 nuts in the top view. The fifth problem is an RCC slab of 2.5 meters square, that is 2.5 meter this way, 2.5 meter that way, and 225 millimeter thick, is lifted by 4 cables attached to the corners, exactly at the corners, and cables are attached to a hook at a height of 1.6 meter above the top, so the top of the slab. So this from here till here, exactly at the center, is 1.6 meters. Each cable has a cross-sectional area of 190 millimeters square. There are 4 cables tied at the corner of the slab, and each and every cable has a area of 190 millimeters square. Determine the tensile stress in cables due to weight of the slab. Unit weight of concrete is 24 kilonewton per meter cube. And here in the same pattern, we have to find out the volume of this concrete, and we will multiply by the unit weight only to get the total weight of the slab. And total weight of the slab becomes the force, and that will cause tension in the wires or tension in the cables. 4 cables are bearing the weight of concrete slab. True. Concrete slab weight equal to 2.5 into 2.5. This becomes the area into 0.225. 0.225 is the thickness. Therefore, this becomes a volume in meter cube. Volume in meter cube, and concrete weighs traditionally 24 kilonewton per meter cube. Therefore meter cube and meter cube will get cancelled, and what we get is kilonewton. Therefore the load of the entire slab measuring 2.5 meter by 2.5 meter is 33.75 kilonewton, which is acting over here in an upward fashion. So in order to find it out, this is the slab, and this is 2.5 meter, and this is 2.5 meter. We need to calculate certain geometrical parameters, and this is the height, and here is the hook going in the upward direction, 1.6 meter, and this is theta, and we need to find the diagonal length. Length of the diagonal of the slab is square root of 2.5 square and 2.5 square. 2.5 square and 2.5 square will give us the total length of the diagonal. That is around 3.53 meters. From here till here diagonally it is 3.53 meters. Therefore length of the cable, we need to consider this particular triangle in order to find out the length of the cable. And length of the cable is 1.6 square, that is the height, and 1.76 square, that is 3.53 divided by 2, that is half the diagonal, 1.76 square, and it will give us 2.38 meter. That means the length of the cable is 2.38 meters. And the system will be like this. This is the force, which is the weight, which is seen as the tension in that particular hook 33.75, and here is 2T, 2 wires from 2 corners. Here again 2 wires from 2 corners, 2 cables from 2 corners. It will get us 2T, because there will be 4T, 4 wires are there, 4 cables are there. Each and every one of them are taking up T. Therefore it becomes 4T. It is common, it is equal among all of them, because the load is very much centric. Therefore if you resolve the force along this, and if you put up sigma v equal to 0 typically, and here actually we have used the fundamental principles of engineering mechanics. We have written the system is in equilibrium. Therefore we will write sigma fy equal to 0. If we write sigma fy equal to 0, we will emerge with this particular expression, 4T cos theta. Okay, here is the tension force acting like this, and this is theta. Okay, 4t cos theta, 2t from here, 2t from here, 4t cos theta equal to 33.75. This is 33.75. Therefore 40 into 1.6 cos theta is here is theta. Cos theta is adjacent by hypotenuse. Adjacent is 1.6, hypotenuse is 2.38, which is nothing but the length of the cable. So that is equal to 33.75. So what we get for T is 12.55 kilonewton. 33.75 into 2.38 and divided by 1.6 into 4. Of course, this particular equation simplified, and we will get 12.55 kilonewton as the force taken up by the cable. Force taken up by this cable. Therefore, stress in each wire is 12.55 into 1000 to make it Newton divided by 190 millimeter square, which is given data. That is the area of cross section of the cable. So this the stress in the cable, typically tensile stress in each and every cable happens to be 66.05 Newton per millimeter square or MBA. The sixth problem is a circular tube of aluminium of length 500 millimeter is loaded in compression by forces P. The outside and inside diameters are 60 and 50 millimeter respectively. A strain gauge is placed on the tube to measure the normal strain longitudinally. If the measured strain is 0.0054, what is the shortening of the tube? If the compressive stress in the bar is intended to be 40 MPa, what should be the load? So stress is given, strain is given. We are asked to find out the change in length, that is shortening of the tube because it is subjected to compression, and we should also find out the load given the stress value. That's all. So strain here is change in length by original length. Change in length is given to be, therefore change in length is epsilon into L, that is strain into L. Strain is given to be 0.54, therefore 0.54 apply into 500. So that gives us 2.7 millimeter to be change in length. Now area of cross section of this particular pipe is particular tube is pi d outer diameter square minus inner diameter square, because it is a hollow tube, divided by 4. Pi d square by 4. Outer circle minus inner circle will give us the area present in the annular region, that is between two circles. So the magnitude of the area is 863.93 upon simplification. And if we further go, stress is P by A, because we need to find out what is the load in order to maintain a stress of 40 MPa. Therefore we know the stress, we need to find out the P value, the force value, compressive force value, and area of cross section is also known to us. Therefore P equal to sigma into A. So sigma is stated to be 40 Newton per millimeter square, because we need to keep this amount of stress within the body of the material. So 863.93, it will give us 34,557.2 Newton, and if you divide this by 1000, we can express this as succinctly and crisply. So that becomes 34.56 kilonewton. Therefore the force applied is, load applied is 34.56 kilonewton, and the area of cross section is given, which will generate a strain of 0.0054. The last problem in this tutorial, the bond between the reinforcing rod and the concrete, that is reinforcing rod which is embedded, is tested by pull-out test. So this particular rod is pulled out, and we will measure what is the amount of force that is required. Okay, a tensile force P is applied at the end of the bar of diameter 10 millimeter embedded in concrete for a length of 500 millimeter. If the pull is 100 kilonewton, what is the bond stress between the steel and concrete? Bond stress and shear stress can be used interchangeably. Of course, bond stress happens to be on the periphery. Shear stress may happen inside the body of the component, or inside the material. material. Here it is superficial. If the rod is getting pulled like this, definitely it will be resisted by the concrete, and the resistance will look like this. So it will be opposing this value of this P, which is trying to pull the rod out. But anyway, the resistance will be developed, and this resistance is none other than shear stress, because it acts parallelly to the surface. So entire circular surface will be subjected to shear stress, okay, over a periphery. Okay, the surface area of the rod is very important, because it is where the resistance against pulling is developed, and this surface area is nothing but the perimeter length of this circular section into this particular length. So if you spread out pi d, it becomes a rectangle, and that is the rectangular area. It is pi d into length. Okay, perimeter of the rod into embedded length. Perimeter of the rod is pi d here till here and here till here in a circular fashion, into L, length is the embedded length. So pi into d is 10 millimeter, because the rod measures 10 millimeter diameter, into 500, which is the embedded length, and what we get is 1507.8 millimeter square is the area that is in direct contact with the concrete. And if this bar is getting pulled, definitely the resistance will be developed over such a huge area. And if you bond stress or shear stress is nothing but the force, that is 100 kilonewton, make it Newton, divided by this area 1507.8. So it will give us 6.936 MPa. We need to pull this by 6.36 MPa. Okay, that is the shear stress that is getting developed. So with this we have concluded. Of course we have to find out the force that is required as per the question. The pull is 100 kilonewton. What is the bond stress that is between? Yeah, we have found out correctly. And the bond stress or the shear stress between the concrete at the interface. The interface is nothing but the peripheral area of this particular rod. So with this we have completed 7 questions, relatively simple, but in the increasing order of complexity. During this tutorial, we solved direct stress and strain problems. Of course, direct stress and strain will not be given. We have to make use of the other data, and we have to find out stress and strain, change in length, etc. And we covered normal stress, both normal stress, shear stress, as well as longitudinal deformation. So this completes the session on problems, and before we come out with the next tutorial, which will contain the problems of little moderate complexity, I bid goodbye to you, all my esteemed viewers. And if you liked this video, kindly subscribe to my channel. Thank you. Until I come out with the next tutorial. Bye. Thank you.